Welcome back to Advent of Code 2017, day 24. It's Christmas Eve. The turkey's in the fridge. What do you eat on Christmas Eve again? It's fish, isn't it? You eat fish on Christmas Eve and turkey on Christmas Day? Not that I really do that. I just eat whatever I want. I don't like roast turkey anyway, it's too dry. I actually would cook a duck instead. But yeah, I think traditionally you're supposed to eat fish on Christmas Eve. Alright, so we're on day 24. Okay, so just 1.5 problems left. So, day 24, electromagnetic mote. CPU itself is a large black building surrounded by a bottomless pit. Enormous metal tubes extend outward from the side of the building at regular intervals and descend down into the void. There's no way to cross, but you need to get inside. No way, of course, other than building a bridge out of the magnetic components strewn about nearby. Each component has 2 ports, one on each end. The ports come in all different types, and only matching types can be connected. You take an inventory of the components by their port types. Each port is identified by the number of pins it uses. More pins mean a stronger connection for your bridge. Okay, so 3 by 7 means 3 on one side, 7 on the other. Okay. Your side of the pit is metallic. Perfect surface to connect a magnetic 0-pin port. The strength of a bridge is the sum of the port types in each component. Right. Fine. So if you had these components, you could make the following bridges. Wait. How many... How many components do you need to make a bridge? Oh, the length doesn't matter? I see. So we're on the left and we're going to the right. You could use one component, which is 0, 1. But I guess it's just really, it could be really long? I don't understand. Chat messages aren't showing on stream? Oh, okay. So I see. So you can actually make a really short bridge, which is just one component. It seems that the length doesn't actually matter. But what does matter is the sum of these numbers. So this would just have a strength of 1, because it's 0 plus 1. Alternatively, you could do this. 0, 1, 10, 1, 9, 10. It's a bit weird though, because that should be the other way. It should say 1, 10 and then 10, 9 to see how they connect together. But that's okay, fine. So yeah, these are all valid. And the strongest one is this one, because it's 31. The sum. So basically, you're trying to. I mean, more is better because that means more, bigger sum. But you know, if you get 10 and 1 and 9 and 10, that sums up to more than 2 and 2 and 2 and 3 and 3 and 5. So it's fine. What is the strength of the strongest bridge you can make with the components you have available? That's how many components we have. Okay, so this is a dynamic programming problem. So, think of a non-brute force solution. Well, what level of brute force are you talking about? Like literally all permutations of these components and see which ones actually match up? You can do a sort of backtracking algorithm where you start with 0, and then you place a component that fits, and then you place another one, and then you remove the last one and place a different one. So it's called a backtracking. It's actually sort of breadth first search kind of. That's kind of not really brute force. That's one step smarter than brute force. But it's tricky to code backtracking. Normally I try to write it in a dynamic programming style, which uses recursion. I just need to identify what it would look like here. So maybe it's not a dynamic programming problem. It looks like we probably do have to do backtracking. Yeah, I mean, so we can do it recursively. We just can't do it in a dynamic programming way, which means you'd only do polynomial number of branches. It looks like we'd actually have to do it the kind of the exponential way. But because only certain components will fit, it probably won't be exponential in practice. But in theory, if every single component was 0, 0, then there's an exponential number of paths you could follow. That would be the worst case, but clearly that's not going to happen, so you're cutting off a lot of branches. So I think just kind of recursion, but it will just work because most paths will actually close off when you can't actually find any more components to add. So yeah, we can do this recursively. The recursion would need to know what our bridge currently looks like and choose what to add. So yeah. All right, let's begin. So we've got the bridge components like that. I guess we should sort to always have the lower on the left. That just makes it unique. Also, are there duplicates? If there's no duplicates, that's actually good. Well, we can check this easily. Okay, so no, why am I putting it here? It goes here. All right, so the line for each line, LR equals int x for x in line dot split on the / character. So let's say we just create a list called components, and we'll put components dot append. So we put min, the smallest value on the left, largest value on the right, and now let's print the length of the number of components we have and the number of components with duplicates removed. Hopefully they're the same. It just makes things a bit easier. It's the same. Okay, so every component is unique, right? We have one of each, do we? We can't use one twice? I guess not, because otherwise we could have done 10, 1, 1, 10, 10, 1, 1, 10. Yeah, no. So they don't actually say, but I guess it's implied. All right, so okay, now what? We want to find okay, we want to define a method. This method will tell us the max strength of a bridge given what number I'm currently sitting on. So 0 to begin with. Every time I add a component, I'm then sitting on, you know, the end of that component. So what's the number what's the terminology they use for this? Port. Yeah, a port. Given a port and the set of components I'm allowed to use, I want to return the max possible strength. Okay. So to do this, we look through all the components, we check which ones match this port, recursively call max strength on what the bridge will look like once I place this component. So the problem is we'll have to keep generating a new comps for every recursive call. That's what makes this exponential rather than polynomial. Fine, we can do that. It's not too big. It's like 55. Yeah, all right. Okay, so for C in components, if C, if the first port, if the left-hand port matches our port, we can handle the right-hand one separately. we want to return so we return, so the max strength will be it'll be the sum of these port values for this component that we're adding plus max, so we have to call max strength given the C1 and it might be better to work with sets here. So if comps is a set, this way we can just say comps minus set minus set of one single item, which is C. So we remove C from this set. That returns a new set without modifying the previous set. And that is the available set to use now. Elif. Otherwise, if C1 is the port, we just do this the same, but the other way around. So then we do C1 plus C0. Same strength, but we use 0. Take away C. Okay. Else. Oh! No. There's something slightly wrong here. We don't return. We have to try all possible C's and then pick whichever was the max. So let's say candidates equals this list. So if cans dot append, so that's one possible strength value of the bridge. Otherwise we do this one. We don't need an else here. So once we've done that for loop, we've tried adding every component if possible. We've put all the scores we got recursively in cans. Now, if not cans, return 0 because there is no possible bridge. Else, return max cans. I think that's it. So we would want print max strength given port 0. We want to take a set of components. Let's try running that. Okay, it's running. Okay, 1859. Let's try that. That didn't take too long. I was worried it could have taken a long time. Correct? But what's part 2 going to be? The bridge you built isn't long enough. You can't jump the rest of the way. In the example above, there are 2 longest bridges. Of them, the one which uses the 3-5 component is stronger. Its strength is 19. What is the strength of the longest bridge you can make? If you can make multiple bridges of the longest length, pick the strongest one. What? Okay. So we just changed the scoring function here. Instead of being the strength, it's going to be the length, a tuple. First parameter being the length, second being the strength. That means I need to modify what I've done. Let's create a new method here. So this time we're doing max length, but we're sort of breaking ties on strength. So hang on, let me think this through. Okay, so we want to take the max, basically the max length strength pair, or should we just call it a score? Max score. Score means strength, length, and then strength as for tie breaking. So we want to return the tuple length strength. So same as before. But, alright, so if we're adding this component, we want to get, so we get the length and the strength to be this. So we find out what the best score is. After adding that component. And the final score will be L plus 1. So we add 1 because that component contributes 1 to the length, and the S value, the strength, will be C0 plus C1 plus S. So it'll be basically the same here. So we would add so if there's no candidates again, we return 0 length, 0 score, let's say. Else return max, and max knows how to handle tuples. It will take the best length first and score. Is that it? Illegal target for... Oh, didn't close the brackets here. Okay. So it should take the same amount of time roughly, because it's not doing anything more complex, it's just different scoring. Right. So we do the first part. And the second part, it says 35 length, 1799. So we want the strength of the longest bridge, is what they asked for. Okay. So we just give the 1799. Correct? Yeah, nice. Straightforward recursion. As long as you code the recursion correctly, it just works like magic. You don't really have to think about dynamic. The tricky part is when you need to do dynamic programming. If they gave us thousands of inputs, then that would probably no longer work. Might not even be possible for this algorithm, this problem at least, but some problems you can identify ways of reducing the number of recursive calls to a polynomial number instead of an exponential number, because you're avoiding overlaps. If the same recursive call is used multiple times, then you make sure you only do that once. But yeah, some problems sometimes you just can't do that. Sometimes it's not possible, but sometimes you can, and then that's what is hard. The hardest problems are the ones where there is a clever way of reducing to polynomial calls. But those don't often come up in Advent of Code, because that's actually considered research level algorithms. This is something real algorithms struggle over. So, but I think once or twice they have actually come up, but usually not very difficult ones. Well, memorization is part of it, but that alone won't solve it, because if I did memorization here, I would still have an exponential number of different component sets that could be called. So basically my memorization table will have an exponential number of key value pairs. So that won't solve the problem, but that will avoid the same the same set of parameters being used twice. Yeah, but it won't solve the problem of there being an exponential number of different parameter sets called. Well, all in all, it's a difficult topic, and that's why dynamic programming is considered to be one of the most difficult topics in algorithms. But cool. Let's see ChatGPT solve it. I think ChatGPT will manage fine. Valid components equals comp for current porting. Yeah, okay. Where's the recursive call? There it is. There's the recursive call. So yeah, same algorithm as mine. Yep, that's correct. And I imagine the second part will be fine as well. So the key here is just they're doing yes, so we're separating out the strength and length. Oh, I'm not sure about this. So he's done what I've done, but why he's keeping the strength and the length separately, and now he's taking the max of the lengths and he's taking the max of the strengths. But those two maxes may come from different components, so I don't think this is correct. Let's see if it works. But you have to pair them together. You can't take independently take the max length you found and the max strength you found. They have to be from the same component. So, I mean, I didn't have a good look at that, but it looks like it's wrong. Please be wrong. I want to beat ChatGPT. 1799. It's correct. I mean, I only glanced at it, so maybe I'm missing something there. So what was I looking at there? Next line. If lengths. Oh, I see. No. It is fine because he's indexing, and he's using the same I there as he is there, so that's fine. Okay. That's Christmas Eve over. Time for Christmas Day. The halting problem, the unsolvable problem. Following the twisty passageways deeper and deeper into the CPU, you finally reach the core of the computer. Here in the expansive central chamber, you find a grand apparatus that fills the entire room, suspended nanometers above your head. You had always imagined CPUs to be noisy, chaotic places bustling with activity. Instead, the room is quiet, motionless, and dark. Suddenly, you and the CPU's garbage collector startle each other. "It's not often we get many visitors here," he says. You inquire about the stopped machinery. "It stopped milliseconds ago. Not sure why. I'm a garbage collector, not a doctor." You ask what the machine is for. "Programs these days don't know their origins. That's the Turing machine. It's what makes the whole computer work." You try to explain that Turing machines are merely models of computation. Well, yes, I guess, but you can make a pretty reasonable approximate to a Turing machine, it just wouldn't be infinite. But he cuts you off. "No, see, that's just what they want you to think." What Alan Turing wanted us to think. It's what he wanted the Germans to think. Ultimately, inside every CPU, there's a Turing machine driving the whole thing. Too bad this one's broken. We're doomed. Yeah, is this the meme? The doomed meme? We're doomed. Okay, I was expecting a different one, but that's also a we're doomed meme. You ask how you can help. "Well, unfortunately, the only way to get the computer running again would be to create a whole new Turing machine from scratch. But there's no way you can..." He notices the look on your face, gives you a curious glance, shrugs, and goes back to sweeping the floor. You find the Turing machine blueprints on a tablet in a nearby pile of debris. Looking back up at the broken Turing machine above, you can start to identify its parts. So we've got a tape, which contains 0 repeated infinitely to the left and right. A cursor, which can move left or right along the tape and read or write values at its current position. A set of states, each containing rules about what to do based on the current value under the cursor. That is indeed how a Turing machine works. Each slot on the tape has 2 possible values, 0 and 1. Based on whether the cursor is pointing at 0 or 1, the current state says what value to write at the current position of the cursor, whether to move the cursor left or right 1 slot, and which state to use next. For example, suppose you found the following blueprint. Begin in state A, form a diagnostic checksum after 6 steps. Oh, it's in words. What does this input look like? Fine. We'll probably just manually interpret that. Alright, so if we run this... So we start in the middle, well, arbitrary position. Begin in state A. Form a diagnostic checksum after 6 steps. In state A. So if one's 0, right 1, move right. And switch to state B. Okay. Seems easy to code. I don't have to parse this, I can just code this. The CPU can confirm that the Turing machine is working by taking blah blah blah. It looks really easy. I don't see any trick, any catch here. What's the 1, 2, 12 million? That's fine. We can do 12 million. It's just a single movement each time. Alright. I mean, my gut feeling is this is really easy, but try and see. And that's... We just have to do part 1. Okay, I'm not actually going to parse this. That just seems like more effort than it's worth. We can just code it. So, let's say state equals A. That's where we start. For in range. So it's going to be that many steps. So, all right. So we need a hash table here. Let's use a default dict. From collections import default dict because it starts at zeros. So tape equals default dict int. So everything is 0 by default. Alright, so we say if state is A. We also need a position. So position equals 0. Okay. So if we're in A, okay. So basically we say if tape pause is 0. Hello, Dr. Onto. Do you do any advent of code programming? So if we're 0... No. Yeah. If data is 0... Sorry to bother you, can you help me in something I'm currently working on? Probably not right now, no, I'm in the middle of a stream. What, is it programming related? It's just an error, but I'm struggling with it. Unless you can describe it in like 2 lines, I don't think I could really look at anything now. I mean, if it has a short description, you could try and I may hit, but I can't guarantee I would know just from a short description. So if we're at 0, place with one, pause, so we move to the right, and change the state to B, elif tape, pause is else. I was moving some photos from my Android to... Oh, this is... Oh, I thought... So this is not a programming question. I mean, okay, I can still... I was moving some photos from my Android to my SD card, but my phone crashed, and now I've got a file in JPG that is like 45 gigabytes. Okay. Is that JPG openable? Is it actually an image? I can't imagine what a JPG of 45 gigabytes would look like. Does it have details? Can you look at the resolution details of it? Or... all the photos mixed together in one single file. It's definitely .jpg and not like .zip or something. Or some sort of compressed thing like .zip, .gz, .raw. It's .jpg. I've no idea, sorry. It sounds like very much a phone malfunction thing, and less to do with file types or compression. And I'm not really good with that kind of phone stuff. But what's the actual problem? Can you just delete it and try copying again, or have you lost the original files? All the images are gone. Did all the images before take up that much space? So it's actually sort of compressed them, but you don't understand how it's done it or how to unpack it again. I don't know what to do, because technically you can make any file and you can make it into a JPG, so it's all down to what the phone has chosen to do, and that's proprietary, so I have no idea what they've done. I can't think of anything else other than contacting well, you can't. You're not gonna get much help from Google because they don't really have any customer service. They're kind of abysmal in that regard. Best bet is to go onto the Android or the phone makers forums and post there and see if any developers are hanging around and will help you. You can try contacting Google themselves, but I wouldn't expect much from them. They try and make it as hard as possible to contact them. Been down that path myself. They want everyone to think they try to boast that they have AI solving all the problems, but the AI doesn't solve all the problems. So yeah, good luck. Okay, so basically I just need to copy and paste each of these. Yeah, no problem. Yeah, hope you find a solution. Oh, thanks for the follow as well. Yep, have a nice day yourself. Alright, so state B. For 0, we write 1. Move to the right. Change to C. Otherwise, we write 0. Move to the right. Still. And go to F. So if we were in C, right, so if we're in 0, we write 1, move left, go to C. So write 1, move left, oops, go to C. So we stay in C, fine. Otherwise, we write 1, still, we write 1, go left still, and go to A. D. So right 0, go left, switch to E. Right 0, go to left, go to E. Sorry, this is in state D. Otherwise, right 1, go right, switch to A. Right 1. Excuse me. Right, and if we're in E, so if we're in 0, we right 1, move left, go to A. Right 1, move left, go to A. Otherwise, right 0, go right, go to B. Right 0, go to the right, go to B. It's very easy to make a mistake here. And finally, if we're in F, so from 0, right 0, go right, go to C. Right 0, go to the right, go to C. Otherwise, we right 0, go to the right, go to E. Right 0, go to the right, go to E. Now, what are they asking for? What is the diagnostic checksum? Count the number of times 1 appears on the tape. Okay. Print tape dot values dot count 1, or just do sum. Count doesn't work there. All right, run. So it's a lot of steps, but 12 million, 4,230. That seems a bit small. Are we very often... So, on average, if you walk about randomly, you're expected to get about the square root of the number of steps you've taken. So the square root of 12 million is, what, like about 4,000? And amongst those 4,000, each side, so that'll be about 8,000. And amongst those 8,000, you'd expect roughly half ones and half zeros, assuming it seems random. So you'd expect about 4,000 ones. Indeed, we've got 4,000 ones. That's actually completely in line with statistical, what's it called? Physics? I don't know. Alright. So 4230. Correct. The Turing machine, and soon the entire computer, springs back to life. Before I do anything, I didn't add the points for the last ChatGPT, so that was a win for ChatGPT. Okay. A console glows dimly nearby, awaiting your command. Reboot printer. Error. That command requires priority 50. You currently have priority 0. You must deposit 50 stars to increase your priority to the required level. The console flickers for a moment and then prints another message. Star accepted. You must deposit 49 stars to increase your priority to the required level. The garbage collector winks at you, then continues sweeping. You have enough stars to reboot the printer. You deposit all 50 stars and reboot the printer. Suddenly, everything seems a lot less pixelated than before. Raise your priority level enough to send the reboot command and, hey look, it's printing. I'll bring it to Santa. Thanks. She runs off. Oh, that's continuing the sentence that she began. What did she say? So at the very beginning, she said, what was the blurb at the beginning of this? Yeah, there must be almost 50 bugs in the system, but nothing else can print the list. Blah, 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 blah. There's no time to explain blah, blah, blah. You'll be able to... And she continued here. Time slowed down while we were in the computer. Raise your blah, blah, blah. Okay. Congratulations, you finished every puzzle in Advent of Code 2017. I hope you had as much fun solving them as I had making them for you. I'd love to hear about your adventure. You can get in touch with me via contact info on my website or through Twitter. Cool. That was good. That was honestly one of the easier of the years I've done. Nothing... One or two of them was kind of hard, but nothing there was really, really taxing compared to some other years. There were like 2 or 3 assembly code programs. I know a lot of people don't like those. I kind of like them, but I do find them difficult, because it requires more skills of interpretation, like understanding the semantic meanings of the assembly code programs. Yeah, it was a good year. Have a look at this. So people found 22 a bit easier. Oh, this one, yeah, that was easy. That was alright. That was not too hard. Yeah, that was actually pretty easy. But these were all roughly equal. Yep. so I am gradually getting closer and closer to being a 100, 200, 300, 400 star holder. I don't think I'm going to get through all these before Christmas, but maybe 2 of them. Good stuff. I can do it. I can do it. It's just a question of whether I want to, because I want to take a break between these sessions, because there's quite a lot of... Oh, what's going on up here? Naughty, nice. Huh? What does this mean? Pararonia is in my leaderboard. Is that... What does that... But I don't have that many people on the leaderboard, but... I've got 2 people in my private leaderboard, Pararonia and Samuel. One of them is here. Who are these other people? What is this? Naughty nice list. Epsilon. Is this from some other leaderboard that I'm in? Because I'm in... Ah, in my Epsilon. It appears to be pulling people from my various leaderboards and putting them into a list. So naughty are people who didn't complete all the stars, and nice are the ones who did. Oh, I think it's just ranking everyone across all my leaderboards according to how many stars they got. And I'm at the top, joint top with Pararonia. Yeah, joint top. That makes sense. And these guys also got stars, and then these guys basically got no stars. They haven't actually done it, but they're at the bottom of the list. Okay. It's funny. Ho ho. E7, E5, E4. DY decryptor. What does this say? While it's a while loop. While 1. That's a while 1 loop. Funny. What's this? IE7E. Oh, this is IEEE triple E. Okay. Alright then. That's enough programming for a while. I think I'll come back on later with Hogs of War, continue with that. I didn't update the title. Okay, that's Advent of Code. I've got to process all the videos and put them on YouTube. Alright, thanks for watching. See you in 2018. Merry Christmas. Enjoy your turkey or duck. I once cooked stingray for Christmas. Traditional Christmas stingray. That was because my neighbor found a stingray in the ocean and he's like, "Do you want it?" And I'm like, "Okay." And then I cooked it. So yeah. Enjoy your stingray if applicable.